Today we are going to have a round table with a couple of guest speakers from two different companies that I work with. I collaborate in some solar photovoltaic projects. In this case, today we are going to discuss around interconnected mini-grids. So mini-grids that are connected to each other and then eventually as well to the grid, to the main distribution grid. Remember, we are following this part of the course is about technology training. So we have seen the introduction. We have gone through the different main components in a PV system, for the generation side of things, the power conditioning, inverters, charge controllers, monitoring systems, etc. We have also seen batteries, storage solutions, and we have discussed a little bit, about configurations. We did a session on off-grid mini-grids, and today we have a session on interconnected mini-grid. Before I give the floor to our guest speakers, I just wanted to put a little bit on the map. Why are we specifying about mini-grids? Well, mini-grids are actually they can have different configurations, different architecture, but I like this kind of classification that was published in a report by RENA. This is the International Renewable Energy Agency, which, by the way, estimates that at the moment there are about 12,000 megawatts of renewable energy mini-grids installed and operating in the world. So around 12 gigawatts of mini-grid cumulative power installed at the moment in the world. So it's starting to become an interesting solution, with considerable capacity deployed. So going back to the table here, you can see in this table 4 types of mini-grids according to the kind of service they provide, whether it is a low level of service in terms of energy or power supply, or higher level of service, and depending again on the power they supply or the energy. And then we can have either off-grid mini-grids or interconnected mini-grids. Today we are going to discuss mostly about what we call interconnected mini-grids in the low to medium, I could say, tier of service. So we're not going to discuss about several hundreds of megawatts of mini-grids like the ones we could have in large cities, or in the US, or in Asia, or in Europe. So we are mostly going to discuss about this type of mini-grids, the interconnected communities or villages or small towns, that can have solar photovoltaics as the main generation source, but sometimes they could have other complementary sources, hybrid generation. They could cover all types of services, critical services, interruptible, base loads, all types of services, so no problem in that sense. They can have they can cover small towns or even university campuses. We have some examples around the world, and even in Nigeria, some projects, and at least one project that I know of in Ghana, in South Africa, etc. And they have obviously some added values with respect to autonomous off-grid mini-grids or grid-connected solutions. There are different conceptualizations about that. As an introduction, now my colleagues Imran and Ivan will tell you much more about interconnected mini-grids, but I just wanted to highlight this conceptualization of the undergrid communities, which is a reality that we find, in some urban, peri-urban, and sometimes rural areas where we have high voltage or medium voltage transport lines crossing the country, which are not serving some communities, some villages that are in between. This is the case sometimes in Mozambique. This is very much the case in Nigeria, where most of these concepts and initiatives are taking place at the moment, together with Ethiopia. We know the World Bank is very active at the moment in Nigeria and Ethiopia, apart from GIZ and other agencies. Okay, so there is a transition. Yeah, this is a process of evolution of different topologies, situations where communities at the moment they are not served, or they are served with electricity through some expensive or not efficient, not even operational solutions that can be eventually connected to the grid, but before they can reach the grid, there's an intermediate solution by developing mini grids, which could be even developed locally with the participation of local or national companies. They don't need to wait for foreign investors to come in. So this is a story of an evolution in the grid architecture. This is a little bit the point I wanted to make. Yeah. So the factor of time is important here, together with different business models. Okay. Imran here, our colleague, will discuss about some lessons learned in Nigeria around these situations on how to interact with the grid. So, without further ado, let's look at the program of today's session. I'm presenting now the session. I'm going to now present the experts. Then we will have a first talk by engineer Muhammad Imran from the company Integration, who is with us now here. Then he will give the floor to engineer Ivan Moreno from Azimuth 360, who will share with us his experiences around configurations and topologies. Then we will have a break, yeah, approximately in an hour's time, or a little bit before. Then both of them, Imran and Ivan, will share with us some mini-grid, interconnected mini-grid project examples they are working on, yes, in Nigeria, in Ivory Coast, in Burkina Faso. And then we will have some space for questions and open debate with all of you, okay, whoever interested. So just a few words on our guest speakers this morning. We are very honored and we are very lucky that we can have them because they are very good experts working in these fields. Yeah, so they really know very well what they are talking about and the difficulties that these initiatives entail. At the same time, these are relatively novel topics. Yeah, even though some interesting initiatives are going on, and in Asia we have some examples we can learn from and try to adapt them to the African context, of course, with all the differences between countries, the different regulatory frameworks we have, stakeholders, map, etc. Mr. Engineer Muhammad Imran, he works for the German company Integration or Integration Environment and Energy. He's an experienced engineer in rural electrification, working in different countries around the world. He has been involved in different techno-economic analysis and development of mini-grid projects, both off-grid mini-grids, but also grid-connected mini-grids or some other systems. So from his office in Germany, he works and he travels to different projects in Asia, in Pakistan, Bangladesh, in Myanmar, but also in Nigeria, in Zambia, in Kenya, etc. And he has a lot of working experience with important agencies like GIZ or KfW, the World Bank, African or Asian Development Bank. He will tell us about the project they are running, the project in which I have also collaborated for GIZ, in Nigeria, where they have been working back to back with mini-grid project developers, trying to bring to reality a number of portfolios of interconnected mini-grids. So this is a very interesting project that I'm very sure we can have opportunities to replicate or to adapt to the context of Mozambique. Okay, so I really ask colleagues today to be very, very listen very carefully to all the lessons that Imran will share with us. This is very valuable. And then later on in this project, we can revisit these possibilities when we approach potential initiatives in Mozambique. So thank you very much, Imran. I'll give you the floor in a minute. I just wanted to introduce our second expert as well, Engineer Ivan Moreno, with 14 years of experience in renewable energy sector, but also the industrial automation. His experience also in fieldwork engineering and project management. So he knows very well about the whole project cycle, yes, around solar photovoltaics. He has worked for SMA, you know, a top class PV equipment manufacturer, especially from the power conditioning side of things. Yeah, so he's very much an expert on SMA equipment among other brands. So he has worked in the sales team and after sales, yeah, as application engineer and trainer. Okay, now he works for Azimuth 360 based here in Barcelona. So we're really very happy to have somebody so close to us who knows the insights of the SMA products. So whenever there are questions or doubts about SMA products, which ones could we choose, not for today, or eventually if there are questions today or later on in this project, we are very happy, we are very lucky to have Ivan with us in the team that can help us address any of the doubts you may have about SMA equipment or possible configurations. Ivan has also participated in many rural electrification projects in Africa and South America. So he knows about dealing with the private sector, which could be very much of use in our project. So I'm going to give the floor now to Engineer Imran from Integration. You have about 20 minutes, okay, for your first presentation about interconnected mini-grids overview, the typical project development stages that you work with or that you recommend, and some lessons learned in that sense. I'll give you, the floor is yours, Imran, and thank you very much for being here this morning with us. Thank you.
Thank you, Paul. Hello, good morning, everyone. It is a pleasure to be here and honored to be able to share this as experience with you today. I'm just going to share my screen. Please allow me 1 second. Paul, kindly confirm if you can see it.
Yes, we can see it very well.
Okay, great. Thank you very much again. So hi, my name is Imran. I am working with Integration, Environment and Energy. As Paul kindly introduced, we are a company based in Germany. And we are working in the sector of renewable energies and decentralized electrification in rural context primarily, increasingly also now in suburban context. And as you can see, we are working all over the world, and our primary areas of focus are Asia and Africa. Integration has been working predominantly in decentralized systems with PV and hydro technology. However, we also work with systems that are dealing with hybrid systems, such as combinations of PV and wind, for example, or now we also have a system where we are consulting our clients on PV and hydro projects. We are basically a consulting company, and therefore we are always very much active in project design, development of projects, and then implementation, support, and monitoring of those projects. I would like to talk to you today first a bit about an overview of interconnected mini-grids, how we deal with them. But before I do that, just taking on the cue from Paul, just want to give you a bit of motivation about the sector. So Integration has been working in Africa, predominantly in Nigeria. In addition, we are working in Zambia, in Ethiopia, Kenya as well. But today I would like to focus the attention more on Nigeria. And just as a motivation, you can see that this is not something new. Mini-grids are actually now quite predominant in Africa, Nigeria being one of those countries. As you can see, there are almost 50 or more mini-grids existing in Nigeria, and more than 100 are actually upcoming. So I hope this can set as a motivation for us today, as a pretext that, you know, this is a booming sector now. And I think for sure, Mozambique is also then on the way to, let's say, joining the party in this case. Just getting back to the topic of interconnected mini-grids, I'm sure as the discussion has been in the morning that interconnected mini-grids are related to those section of the mini-grids where the supply is also not considered to be very critical. However, there is still a base case supply that is needed. Furthermore, the idea or why do we need mini grids or what they can help us. I just want to use this illustration to make this point a bit clear. So for example, in a lot of countries, not just Mozambique or Nigeria, we have situations where there is a main grid. However, it is not being able to supply power to the communities successfully. There are several reasons for that. One of those is that, there is a problem in revenue collection. There are losses in the system. So there is a financial losses in the system. And then there are also technical losses. And what this means is that the main grid is not able to supply the local grids adequately. And eventually the communities end up using have a high dependence on alternative fuel supplies, such as diesel fuel, or if there are other alternatives, burning fuel, wood, or other alternatives, which are in fact at the end not very sustainable for the environment, but also have a high cost for these communities to meet their electricity needs. How interconnected mini-grids can solve this is that it is an addition of generation at a local grid level. So compared to big power plants like megawatt level power plants or hydropower plants, interconnected mini-grids solve these problems by having localized, small PV-based or other hybrid renewable generation. It can be complemented by a diesel generator as well. But this additional generation on a local level allows that the community can be provided electricity via this supply, as well as benefiting from the supply whichever is coming from the main grid. One possible model, for example, is that there is a new developer or an investor who is coming in and investing in the sector and saying, I'm then responsible for the local grid and I make it stronger by bringing in my own generation. There are different models how this can be regulated, and I think we are going to talk more about it in today's session as well. Just as a schematic of how such a system would work is, for example, you can see that these are the target customers eventually. At the moment, they are only receiving electricity from the grid. However, there is an option to build a mini grid. As you can see, you have PV module, an inverter, you have a battery inverter, and then a generator. This would be a typical mini grid. But then you have an option to connect it to your connections, either to the mini grid or the houses can be supplied electricity via the grid as well. And eventually, in advanced cases, you can also have the mini grid or the interconnected mini grid feeding power to the grid as well, if the regulation allows for that. In terms of the electricity supply strategy, how this is beneficial. So the idea is basically that you would design a system which is benefiting from renewable generation during daytime. So you will have PV-based systems in, for example, where you will focus that you are trying to meet your day demand using PV and trying to reduce your cost on batteries, because you know that there is some level of grid supply potentially available. So that you can discuss with the grid supplier to say, okay, I will make a system which caters for daytime supply using PV. I can save my cost on batteries, but then I would buy power from you during the night time. This is one strategy that we also see in Nigeria, for example. Important for such a system is that then PV from the local generation has precedence and is able to provide this electricity to the households, so that there is an incentive to build this system. And of course, then there is a facility to optimize such a system using different tariff regimes. So you could have a different daytime tariff and a different nighttime tariff, so that people are incentivized to use PV electricity during the daytime. Such an activities such as welding or other supply activities can then take place during daytime. The grid in this case, I'm sure my colleague Ivan is also going to talk about it, that these systems, whenever it is working only with the mini grid, the system is being operated as a mini grid and is being formed primarily by the PV inverter, or in case when the PV is not operating, even a generator can also form the grid and supply electricity. So it's a very robust system, and depending on what is the requirement and what makes sense financially as well. During the night, as we said, that you would consider a certain level of usage from the grid as well. However, you could also have grid supply complementing it. And what we have seen, for example, in cases is that at night, primarily the generator is providing electricity to the people. However, whenever there is grid supply, which is usually cheaper than electricity from the diesel generator, so that system can leverage from such a facility and provide optimal power to the people. Now, I would just like to walk you through a typical project development cycle. What are some of the stages in, let's say, designing and developing a interconnected mini-grid project? So at integration, we are working with our electrification planning toolkit, and this is our concept, how we deal with such systems. Just as an overview, we have a few concrete steps. The first is identification of the site. Which is the right site? How can we tell should we proceed with the system or not? Then we do some remote mapping of the location. I will talk more about it, the tools that we are using to be able to, before putting foot on the site, be able to have a first idea of what is the community like, what is the structure. Then there are definitely, you need to be on ground and collect some data, conduct surveys. Based on this information that is collected, there is a demand model that is created to identify what are the demand profiles. And we are using that to do a generation system sizing on one side, and at the same time, a distribution network sizing for the system. And finally, both of these are feeding into a financial model for the project, and so that we are able to say under which tariffs this can work. Now, I would just like to show you a few further steps. So the first step, as I said, was this detailed remote mapping. So what we are usually doing is that as soon as a site has been identified, we are using open source tools like OpenStreetMap and other satellite imagery to map those buildings. So you would have a community, you just go there online, and then you use those images to say, okay, this is a community with 500 households, or this is a community with 2,000 households. And that has an impact whether it is a viable system or not, and also can dictate what kind of levels are we talking about. So for example, if you have a community which has 5,000 or more connections, you immediately can say that, here we will probably need like a medium voltage network. Whatever data that we are collecting is also uploaded on OSM, which is the OpenStreetMap, and is then available for other projects in the sector, for example, humanitarian projects. At the moment, this could be also COVID relief efforts. Then they know where are the communities, what are the main community centers out there. In the second step, like I said, we are going to those sites and collecting information about specific users. Experience has shown that it is quite vital to actually geotag the locations of the large consumers, because then you know that this is the main community center, here is the church, here you have a barber, for example, here you have a store, here you have a welder, because this will then in future have an impact on how the grid is to be set up, or if an existing grid is there, how it can be improved. There we are also using a lot of GIS-based survey tools so that the expert can go on site, geotag the location, insert some information about it, using a mobile form or something like that. And when they are coming back into network, the information is automatically synchronizing. So there we are using tools like Coco Toolbox, which allows you to work in offline mode when you're there to gather all this information. A very important part of this is also to collect information about the existing grid on site. Since this is an interconnected mini-grid, we must know what is existing out there and what is the condition of that equipment, because that will dictate how much of the existing grid needs to be rehabilitated and what additional grid needs to be built on site to make the system operational and function well based on the requirements that we have. Therefore, they have two aspects: demand assessment and also the assessment of the grid on site. Once we have done that, we are usually creating demand models, whereby we are creating these typical demand profiles and having a first idea, like I said, about what is the condition of the grid, how much of it can be used, how much needs refurbishment, and then provides us an idea, okay, this is the peak demand of this system. This is what the demand profile is looking like. And it can give you an idea. For example, here you can see that there is considerable demand in the evening hours as well. And this gives you an idea that, you know, just a PV-based system is not going to work for you. A typical PV profile is during daytime. So you need to think about options with a nighttime supply, either via batteries or diesel generator or grid supply. And that awareness helps you to get a first idea of what the generation supply could look like. So based on this information, we are then moving to the next step, which is the generation asset sizing, where we are using standard tools like Homer Pro that I think is now an industry benchmark. And then we are comparing different scenarios. So for example, here we have two scenarios to say that if we want to supply the same community with grid supply, then without grid supply, for example, in the first case, we will need a system of 240 kilowatt peak, and you will need a battery bank of 150 and a diesel genset of 130. However, in the same system, if we are able to integrate grid supply of 4 hours, then the things change a bit. What is changing is, for example, you can see that the fuel usage is going down from 69,000 liters per year to only 40,000 liters per year. And this has definitely an impact. Like I said earlier, grid supply is cheaper than diesel supply. Electricity supply from diesel. So you can also see that the levelized cost of electricity is going down in the case when we have at least some level of grid supply. Based on experience, we have also seen that even 2 to 3 hours of grid supply can have a big impact on making these projects much more viable and cost effective. Then we are basically coming up with these supply profiles. As you can see that this is the generation PV supply. But based on our demand that I showed here before, we see that in the early morning hours, they are being met by diesel. There is some supply from the main grid during the morning hours. Then our PV system is able to supply it. We have a certain level of storage here. And then again, a big chunk is being supplied by the grid here. And just like I said before, if the grid were not there before, all this would have to be met either by batteries, which are expensive, still expensive compared to grid supply, or supply by a diesel generator. So, but this kind of optimization can help us to come to a system that we can proceed further. It also then tells us what are the supply sources, how much of it is renewable, how much of it is based on conventional grid supply. At the same time, we look at the distribution network layout. And there we have several possibilities that you could have a centralized network. That is, you have one power plant, which is providing your big area. However, if you have systems at low voltage, for example, then you need to consider the boundaries conditions as well. For example, a low voltage system is typically up to 1 kilometer or something. And if the system is becoming bigger, then sometimes it is even advantageous to break it down into 2 subsystems. And what we are usually doing here is that we map the community, as I showed before. We map the location of the transformers. And usually the grids are structured around transformers. So there are subnets in the network. And we take them as a basis for us to say that this is the first area around one sub-network based on a transformer location. And this is the second area. A key important parameter of this is to prepare these interconnected mini grids in a way that they are compatible with grid supply as well. Just like I showed before, grid supply is a key component of an interconnected mini grid system. Therefore, the grids that we design, the distribution network, needs to be compatible with the existing grid and be able to absorb power from it whenever it is available, and eventually also being able to provide to it. That means that we also have to plan for circuit breakers and further safety devices at transformer locations, and also if there is a need to install bulk meters to allow for further recording of the units that are being transferred from the grid or the other way around as well. Based on this first analysis, we are doing a grid simulation, and then you can see that we get an idea about what are the areas in the grid where you have a higher demand. That was based on our initial tagging of the connections, where those barbers were, where were those welding facilities. And this gives you an idea of what the cable sizes need to be in different regions of the community. And since we have done an initial mapping of the community grid, where it is existing and where in which condition it is. We are able to tell that, you know, this is the main road in the community. At the moment, you have a 35 millimeter square aluminum cable. But because now we know the demand of the community, we feel that it needs to be upgraded to 70 millimeter square diameter cable, or maybe even higher. And this kind of information is then used to say that this is the grid that needs to happen eventually, so that you are able to then calculate what are the upgrades that need to take place in different areas. And therefore the engineers on site, or the company or the team that is implementing it, will have a plan to say, okay, here the grid is running, this is where the new grid will come, and this is where it can stay, and this is where I need to rehabilitate it or strengthen it further. Once we have this information, it is feeding into a financial model where we are basically looking at CapEx cost, that is the main investment cost that is going into the project, the OpEx cost, which is the running cost. And as you can see that if we had used less diesel fuel, that means your operating costs are lower. And then we are basing it based on the required IRR, which is the expected profit out of this project. And that is helping us to come up with a tariff that we can offer to the community, or the project can offer to the community, or in case the project needs financing to become viable, which is at the moment, it's still the case for most of these projects. We are able to make an estimate of what is the viability gap. And what this means is that how much money should still need to come in the form of a grant to make the project still worthwhile, and to make an investor to make the project attractive for an investor to come in and invest in the project. What we usually see in the industry is that you have, at least for now, structures which says that, you know, there is about 60% share of grant in these projects. You have about 15 to 20% equity in such projects, and then the remaining is met by debt, raised either locally or internationally, depending on the context. What you also see here is a typical cash flow analysis that we are doing using standard Excel-based financial models that can tell you, okay, this project is going to break even after year 7. And then this is how the projection is looking like. One very important thing here to say is that mini grids are there for a while now. And the expectation in the industry is that they are going to reach their break even after year 3 or year 4. Unfortunately, that is still not the case. And the sooner we realize this, the better we are able to accept that and adapt to it. It's still project life break-even periods of 7 to 8 years are common. And that is also considering that the OpEx are not running over time. But then you can do sensitivity analysis and to see, okay, if the diesel is changing, what does that mean and how does that impact for us? Just to wrap it up a bit, so you can see that a typical project development cycle would start from a mapping of the community, that, you know, this is the community, these are the connections. The next step would be to go on site and collect actual data about the people, the connections, and the grid which is there. Both of this is then feeding into us making a demand model to find out what is the demand needed, what is the demand profile looking like. This is then being used to design the generation system, the supply strategy. At the same time, it is then being used to design the distribution network layout, to say what the grid needs to be able to meet this demand. And all this is then culminating in the form of a financial model that tells you what the tariff needs to be to make this project viable, and what is the return of this project, and how many years is this happening. This is more or less a typical project life cycle that we see in interconnected mini-grids. Like I said, the key distinction is that in addition to the typical work that is happening in a normal off-grid project, there is a strong focus on always considering the existing grid out there, so that you can use it in your planning for the generation system, in your planning for the distribution system, and can have an impact on how the financials of the projects are looking like. So that is it for now. Over to you, Paul. Thank you.
Thank you very much, Imran. Oops, okay, here I am. Thank you very much, Imran, for this presentation. And later on, after in about 20-25 minutes, we'll go back to the examples, and then you can also continue sharing some of the experiences in Nigeria, specifically for the
Happy to do so.
as project with GIZ. Thank you very much. Okay, now it is time for engineer Ivan Moreno. I'm coming to share a presentation myself. Just give me a second. Okay, here we go. I'm going to share the screen now. And then, Ivan, you will be able to start in a second.
Okay.
Okay, Ivan, the floor is yours. You can start.
Okay. Thank you very much, Paul. Hello, everybody, and thanks for this nice introduction. I'm very pleased to share this time with you. And sorry, my English is a bit bad, but I will try to do my best. Many thanks, everybody. So we are going to talk about mini-grid topologies, comparison between it, and also we will talk about strengths and weaknesses in regards of centralized generation versus isolated mini-grids, and some technical aspects as well about the equipment typically used in these kind of installations. In the next session, we will compare two projects of isolated and centralized models. So going to the typical mini-grid configurations, in the next slide, we can see the classical approach, which is a typical grid extension to rural villages. Here we can see the classical approach is when we have a national public grid, so-called utility grid. So we can find the transmission grid and a sort of backbone medium voltage distribution lines deployed to reach each site, and so those villages will have their own step-down medium voltage transformer to match the low voltage grid inside of the community. So this is what we found in many of the countries, and it's a typical grid extension model. So there's no much.
Sorry, Mr. Ivan.
Yes.
We can't hear you properly.
No. Paul, do you listen to me?
Yes, but it's a little bit. It's a little bit far away, I think, from your microphone. If you can perhaps speak closer to your microphone.
Yes, thank you.
If I try to speak a bit low, in this case, do you listen to me? It is better now, or
a little bit better. I think yes, if you can speak closer to the microphone, or
I will try to use
okay, that's a good idea. Yes, let's try with the.
Mr. Ivan, if you have problems speaking English, why you don't speak Portuguese? It will be quick for us also.
No,
Portuguese, it's not possible for me. Sorry.
In Spanish.
Oh.
Okay, you are Spanish. Okay, fine.
In Spanish, yes.
No, this is much better, I think, Ivan, now.
The sound is better?
Yes.
Okay, good, nice.
Much better, thank you.
Yes.
Okay, perfect. So going back to the presentation, in this, okay, here we have it. We were talking about the classical approach models, but when we have typical grid extension to rural villages. It is medium voltage distribution lines, and each village has its connection to the medium voltage line with a medium voltage transformer. So we step down to low voltage grid inside the community. This is the classical approach. And in the next slide, here another classical approach is an alternative approach that would be in the absence of a national grid between the different villages over the territory, and those sites have developed their own energy systems for the supply of electricity, sometimes with generators based on fuels, but typically renewable energy is based on photovoltaic technologies. Here we can see each town has their own PV plant or mini grid with batteries, and also we can see in some cases for isolated villages that has no resources, no PV resources yet, so they can connect to another village that has these resources, and we, by means of a medium voltage distribution line, could share these resources and this electricity produced. So that's the case. We can have simple or small towns with their resources and some others sharing between them. Yeah, here, so that's what we call mini grids, and could be managed by one operator, for example, with the same tariff for all consumers, and managing the service and maintenance tasks with a small team of technicians, but all over the same business model. Because these case situations may be the same in each village regarding these PV resources. So this is another classical approach when we have different hybrid mini grids. Okay, next slide. In here, in this slide, we can see again the classical approach of grid extension scheme to fit several villages, each one with its own medium voltage transformer to step down the voltage. And in some convenient point, a big PV plant is installed and connected to the medium voltage distribution line by means of a medium voltage transformer again. And in this case, these projects sells the energy to the utility grid operator in a feed-in tariff model, for example. So we have here an example of large-scale grid-tied PV plant providing energy and supporting the utility grid for the whole community of villages. So here the benefit is to have a one-only PV plant, and it's easier to manage. But this is a classical approach when we have feed-in tariff, and the business model is to sell the most amount of energy possible, and then the whole community benefits of this part of energy that is produced by PV resources. Yes, it's a classical approach as well. So in the next slide, here we have another example. This is called interconnected solar mini grids, when we have a concession of low voltage distribution. As shown here, there is a utility grid again. We already have some grid extension scheme with several villages, again interconnected as seen in the classical approach. But in this case, there are concessions to install PV generators in different communities, connected to the low voltage lines of the villages before the step down medium voltage transformer. so that they can use both electricity from the utility grid as well as the produced energy in their own PV installations as a self-consumption model. In this case here, we see there are meters in each community that have a PV plant in order to do net metering whenever is possible, or also to control the plant in case there is no chance for eventually feeding the utility grid with a surplus of energy, which is not consumed in the village. It is typical to have the situation that we produce an amount of energy and in every moment there is a load consumption that is different from the production, and sometimes we have surplus of energy, sometimes we need to take energy from the grid to in this we have the chance to feed in the surplus of energy is very good to avoid losing energy that we could produce and share with other communities. In this scheme, we can see that if the net metering is possible, the surplus could be shared with other communities. Here we can see there are two of the communities that doesn't have PV resources. So well, all the surpluses of the different sites could be shared and improve the electricity feed provided. So always it's better to share or sell the energy surplus instead of modulating and reducing the plant production to fit the current load consumption. And also here we could have contracts with the utility if we have the meters to do that. So in this scheme also we can have big PV plants as seen in the slide in the previous slide, sharing this feeding in the utility grid, and then the solar fraction is bigger. No? We can have both situations, big PV plants in the place it's better to have a large scale PV plant, and also every village have their own resources, so that we improve a lot the self-consumption of renewable energy. And in the next slide here, we have another model of interconnected solar mini grids, which is the management of a medium voltage distribution. When there is a model already developed that is an evolution of several mini grids that have been progressively interconnected to the main grid, and then it's possible to come to this model of medium voltage distribution management. If, for example, if it's possible to do net metering with one only meter in medium voltage measurement, and so that this can bring the possibility to balance costs in a common tariff, for example, for all the consumers, and therefore to get the benefit of sharing all the energy generation, the green energy generation, among the community of villages. This is the same as that we've commented in the previous slide, but in this case, only with 1 meter is easier. Then this more optimal scheme for the renewable energy optimization, because here we don't need to have contracts in each village, and the share of the surplus is automatic or is easier, and so we have only one point of interconnection with the meter, with the medium voltage line. So this is the evolution of the previous slide, and that could be, well, a kind of net metering with various communities. So here we can, now we're going to talk about the strengths and weaknesses of these two business models, the centralized generation and the isolated mini grids. We can think into different strategies. In one hand, we can provide each village with PV resources, as we have said before, and support of the utility, having this support of the utility or the field-based generators, so that would be the interconnected mini grids. No? Each mini grid with their own resources. And on the other hand, we could think in the centralized model, centralizing the PV resources all together in one site, and then deploying medium voltage distribution line from that community to reach other villages, the community where they have the PV plant, and other villages that doesn't have PV resources yet, as we've seen before. They can benefit of a medium voltage distribution line to have this electricity produced and shared with the utility. And here we are going to talk about the strengths in these two cases: the centralized generation that could be with interconnection to the utility grid, or without the utility grid, with gensets or fuel-based generation. And in the other hand, we have the isolated mini grids that could be also interconnected to the utility if there is an existing one, or isolated and with their own auxiliary systems, like gensets, as we've seen. So here we can see we are starting with centralized generation. What is the pros? In this case, we can see optimization of the components of the photovoltaic installation due to the factors of simultaneity and use. It's clear we have only one side with a PV resource. It's easier to manage. Then we have only one single point of interconnection with the national grid, which also is a good point, managed by a single meter and eventually a sales contract. That is always easier than having several of those contracts and points of interconnection. It's also, we have only one auxiliary generator needed. So, as you know, generators have maintenance and cost, and so if we have only one unit or some gensets, but in the same place and in the same installation, it's easier to manage the operation costs. Also, you can see that, well, this optimization of management and operational maintenance costs related to all these components in the installation. Also, technical or facility management improvements affects all subscribers equally. This is a good point. Any improvement or well, improvements in the installation affects to all the subscribers. So this is the case of centralized generation. Also, operation for replacement of components at the end of the useful life is more optimal. Of course, we have everything in the same place. We could send devices. If you have only one point of logistics, it's always easier, as you know. in complex places to transport devices, it can be a nightmare. And so these are the main pros points regarding the centralized generation. If we go to the several mini grids situation, there are another good point is that in the event of a breakdown or a failure in some of the systems, only the partial number of users is affected. It is clear. In the other model, if there is a breakdown or any kind of important failure, you lose all the plant, or you have a big problem with that plant. So all the countries all the villages are affected of this breakdown. This is clear. This is a good point for the mini grids. Then you also have less hardware regarding the transformers required to connect these plants to the auxiliary support of the utility grid. As you can see in the left side with centralized generation, we have to use always step up or step down medium voltage transformers in case of distributing, connecting to isolated areas to that centralized plant. And in the case of several mini grids, you don't need to, if there is no utility grid, there is no medium voltage transformers. But if we have it with a national grid, then we just connect each of the villages to the medium voltage distribution lines by means of a one only medium voltage transformer, which is also good. But well, this is the case of well, this is the case of the less medium voltage transformers. Also, medium voltage grid maintenance work is done by the electrical distribution company, which is also a very good point. In the case of centralized, and you have a branch of medium voltage distribution, you have to take care of all this hardware and this installation. So in the case of isolated, the distribution company is taking care of the expenses, the cost of the maintenance of the medium voltage line. And also the low voltage grid maintenance work is less complex and dangerous than in a medium voltage line, of course. And easier to be performed by local technicians. In the case of isolated mini grids, the complexity of the system is lower, and it's easier to find technicians or to manage this level of hardware. In the centralized model, we will have medium voltage always in some way, if there is a utility or not. And so this is a good point as well for the isolated mini grids. Okay, and the next slide we can see the weaknesses of these two models. In the case of the centralized generation, we have transformers mainly increase losses in the distribution lines, big transformers, which must be compensated by increasing the photovoltaic generation capacity. We always have to take in consideration the losses of the medium voltage transformers. It's clear at this point. And also the transformers and medium voltage lines may increase the investment cost. Of course, this is always more expensive than low voltage installations. And in the case, the next point is that may increase the maintenance cost. Of course, as well, the medium voltage lines need also this maintenance, and is not that easy compared to the low voltage. Also, another point is the technical complexity and working safety measures. That's the same point. Due to higher voltages of the lines, you have to have a special preparation for managing medium voltage installations, and it's not easy to find specialized technicians in this. Is the next point. It's difficult to find local technicians trained to work in medium voltage lines, but if it is needed, it needs to do a training, and a small team of people could be specialized in these medium voltage lines. These are the main cons, weaknesses, points of the centralized generation. In the case of several mini grids, the total sum of the different components of the facilities is higher than for centralized case. Of course, the different points, different installations, and sizes of everything means that there are many components. In the centralized model is less complex. The PV resources are more clear. Just one installation. Well, also we have higher investment in civil works. We need sheds, fences, monitoring, internet connections for each and every point or isolated mini grid. In the centralized model, we have only one part of this civil works, only one installation. So that means easier or less investment in civil works. Also, several points of interconnection with the national grid needed. So several meters and sales contracts, as we have talked before. This is, it's easier to manage only one contract and only one meter in medium voltage measurement than having many contracts in different situations. No? Also, you can have several generators. Each of the installations need their auxiliary supply, because batteries are expensive. They need to be taken with care. So we always need an auxiliary supply in the case the battery is low. So then we have several generators, and that means a lot of maintenance, and you know, then we have higher fixed for management of operation and management costs. It's clear we have different villages to do the maintenance and operation of their resources. It's more complex to manage a team or to have the proper resources to do in each site when they need those services. Also, the components replacement at the end of their useful life may not be synchronized, so it's more expensive because you know the installation and transport it increases and gets complex to reach some isolated areas. So in a centralized model, it's quite easy. The logistics are always easier than the small points or villages. Also, we have uneven results. Some systems may be oversized while others are undersized. This always happens. We never know the future or situation of those villages, and sometimes the expected growth wasn't considered, or well, we have different installations, so it's clear that we have to size the systems for each case. For interconnected mini-grids, also several meters are needed, one for each mini-grid, which also involves more management complexity and higher fixed purchase costs. And this is clear as well. And then for isolated mini-grids, using several auxiliary generators will increase operating costs, as we have seen, since the energy obtained by the diesel is more expensive and a greater number of hours of use means higher costs of operation in compared to the centralized model. So these are mainly the cons, the weaknesses of these two different models. So I think Paul wants to make a pause, no?
Yes. Thank you very much, Ivan, for this talk about the configurations and topologies. Thank you very much. I hope now the sound was better. At least I could hear you very well.